Let's go over problem Q, flowers from Atcoder educational DP contest. This is problem Q. The problem statement is that there are n flowers arranged in a row. For each I from 1 to n, the height and the beauty of the ith flower from the left is h of I and a of I respectively, and all the heights are distinct. The arrow is pulling out some of the flowers so that the following condition is met. The heights of the remaining flower is heights of the remaining flower are monotonically increasing from left to right, and we need to find the maximum possible sum of beauties of the remaining flowers. So let's ignore the thing that he's pulling out some of the flowers, and just say that we need to choose a subset of flowers so that their heights are increasing. So let's say we choose the 2nd, 7th and 10th flower. Then h2 should be less than h7, should be less than h10. This is the condition. If we choose 7 and 10, and in this, for this choosing, we get a score of a2 plus a7 plus a10. So we need to find the maximum possible attainable score for all the subsets, right? This is the question. The constraints are n up to 10 raised to 5, 2 into 10 raised to 5. Heights are bounded by n. It wouldn't have been mattered, but let's see how it is helpful. That heights are only up to 10, values up to n. And again, the scores are positive and up to 1 billion. So let's go over some of the observations. As I mentioned, we need to find a subset. H of I are increasing and sum of A of I is maximum. This is the main construction. So for any dynamic programming approach, we need to know what we are actually constructing and what we are trying to find out using that construction. So construct any subset, we start with, or we need to construct a subset, and we will initially start with any one element of the array. Let's say we start with index I. It could be from 1 to n, anything. So if we start with I, next we can take any j which is greater than I, because we need to take a subset from left to right. And let's suppose we take this one. There are multiple choices, but the main idea is to choose a subset from left to right. We first choose I, then choose j, and the condition for j is that the height of the jth element is greater than the ith element. So height of j is greater than height of I, increasing, and in this case we, let's say, get a score of a of j, since we have included that in the subset. And this straightforward approach will take order n square time. So we are going to fix I from 1 to n, then we are going to go over all the j from I plus 1 to n, and we update the TP value for jth index, right? So in all, this will take order n square time, and we need to do it faster. The recurrence relation that we obtain from this observation is we are going to do, in this approach, I assume that we go from I to j, but in iterative dynamic programming recurrence relation, we are going to say that to arrive at an index j or include the element at index j in our subset, we are going to basically go over all the indexes j, which could be possible for the previous chosen element of this subset. So if we choose I in our subset, then previously we could have been chosen any j which is which lies to the left of I, and the height of that element is smaller, and it lies to the left of that element that we are updating the answer for. So this is the straightforward recurrence relation, and this naive implementation can take up to order n square time, as we saw. And so this recurrence can be updated a little bit. So if you observe, heights are only up to 0 to n, right, as we saw in the constraint of the problem, and we can basically change the subscript of the DP array. We can store the heights here, right? If we store heights here, then essentially we only need to update the answer for any index I. Initially we are going to update the answer from all the index from left to right. We are going to update the answer for dp of I from left to right, and to update the dp of I, we essentially update dp of h of I, and this simplifies because we eliminate the iteration of going over all the indexes j less than I by considering all the previously chosen elements with heights in this range. So we want h of j to be less than h of I, hence h of I belongs to the range 0 to h of I minus 1, since it's less than the height of the index that we're considering, and we're going to solve it from left to right. So this is basically a continuous range. So we need to find the maximum dp value in this region. In this, suppose we want to construct find the answer for this index, and we know dp values for all these ranges, heights for all the heights for the elements in this range, and we can query the best dp answer in this range, which is basically a fx of dp array. And this can be done using bit or segment tree, as you like. In my implementation, I will be going through the Fenwick or bit implementation. So let's see the implementation. Okay, so this is the struct binary index tree. This stores the values, and this is the size of the bit. Initializes the size and the default values for all the values for each index in the range 0 to n. And initially we only need two types of functions, which is updating or changing the value, like dp of idx is changed to dp of I max of max with val. So this is the operation that this function will perform, update max at position idx. I don't want to go into details. You may read about this data structure in depth on another blocks. And prefix max will basically return maximum value in the range for the dp values that we are storing in. Since this is a prefix, so we'll get the maximum in this range. Both these two functions are helpful to update the maximum value and query the maximum in particular range, which is what we want to solve this recurrence. Now let's see the implementation. Okay, we input n, we initialize the dp array, and again here input h and score array. Then we solve the answer from left to right, 0 to n. The best answer that is possible at a particular index is basically to either choose the ith element. So we'll choose the ith element, and we are going to find out what is the best answer. We choose I in a subset which is earlier chosen, and basically I'm updating the dp with d of I because I can say that I don't want to include any other element in the subset. So this was the first choice and this was the second choice. First was to extend a previously chosen subset with I, and second was to take the single subset I. This is because this may return minus infinity as a fact that there is nothing in this range, nothing in this prefix. So this may become -1 for a height equals to 0, right? Or it may become 0 and the EIT only supports positive indexes. In that case, this may return minus infinity. So we also need to handle the case that this best also accounts for this individual element as well, and then we update the best at dp of h of I. Since we are updating h of I with best, as we saw in the explanation, when we change the recurrence to dp of I to dp of h of I right here. Initially we are using dp of I and we change the subscript to h of I. This helped us in querying the maximum in a particular range to by converting it to a prefix maximum problem, and basically update the answer for the best possible answer at each index. So answer is basically, this answer is max for all the dp this range 0 to, and since heights are in this range, so this line will take care of that. That's it about this video. This was a easier problem and I hope it was helpful. Do let me know if you have any doubts or queries in the comment section. Thank you.